Afternoon, everybody. You're in the Jasmine Ballroom, and our next talk is Discovering and Exploiting Novel Security Vulnerabilities in Apple ZeroConf with Xiaolong Bai. A couple of quick announcements. If you haven't already, stop by the Business Hall located in Bayside AB. That's down on the first level. A lot of vendors there to check out. The Black Hat Arsenal is on the Palm Foyer on level 3. That's this level, just past the escalators over there. And there'll be a reception there in the Arsenal about 1700. So definitely want to check that out. If you haven't checked out the Black Hat Swag Store and the bookstore, that's on the second level below us. Today's the last day to get your merchandise. And then also there's a Kali Linux lab in Mandalay Bay A. Again, that's on the second level, all the way back, not by this escalator, but back by the other escalator. So you want to check those out. If you haven't already, please put your phone on silent so you won't interrupt our presentation. And with that, I'll hand it over to Xiaolong.
Thank you. Hello, everyone. Today we are going to talk about discovering and exploiting novel security vulnerabilities in Apple ZeroConf. This is joint work by Tsinghua University and Indiana University Bloomington. My name is Xiaolong Bai. I'm a PhD student from Tsinghua University and the System Security Lab, Indiana University. This work is led by Lu Yixing and me. Other authors include Nan Zhang, Professor Xiaofeng Wang, Xiaojing Liao, Tongxin Li, and Professor Shiming Hu. Before showing our research, I'd like to introduce who we are. We are from the System Security Lab, Indiana University, Bloomington. We are a group of motivated researchers working on system security. We focus on novel problems in system security, including but not limited to the security of Android, iOS, big data, cloud, and health informatics. On this Black Hat event, we have two talks. Besides our talk, our collaborator Nan Zhang will also give an interesting talk today. We are looking forward to your participation. So let's begin our talk. Our talk is entitled Discovering and Exploiting Novel Security Vulnerabilities in Apple ZeroConf. So today we are going to share some vulnerabilities in Apple systems, including iOS and OS X. But here is the question. What is Apple ZeroConf? ZeroConf is short for Zero Configuration Networking. It is a set of techniques that automatically configure a usable network. With the help of these techniques, there is no need for manual configuration or other specific configuration server. These techniques are designed to reduce users' burden when setting up a new device or using a new service. So when we talk about zero configuration, the first concept I'd like to introduce is Bonjour. Bonjour is a protocol of zero configuration networking over IP. Apple has submitted Bonjour protocol to the IETF. So with Bonjour, Apple wants to provide the capability that with little or no configuration, users can easily add a new device or new service to a local network. And the existing devices can automatically find and connect to these newly added devices or services. So with Bonjour, administrators no longer need to assign IP addresses, host names, and service instance names to the services on a local network. And with the help of Bonjour, when users want to use a new service, they simply ask to see what network services are available and choose from the automatically discovered services. In order to better understand what is ZeroConf, let's take a quick look at the traditional network that requires your manual configuration. Traditionally, you cannot connect to your printer without proper configuration. You have to manually configure the IP address, printer name, or DNS records in order to connect. However, in terms of usability, people don't like such manual configuration. We want everything to be automatic. So we have Bonjour now. We want a service to automatically configure itself, and including its IP address, hostname and service instance name. Also, we want the users to have the ability that they can automatically discover available services in the local network without pre-knowledge of the service instance name, host name, or IP address. So how is Bonjour working? We will take the printer as our first case. We will first show you how Bonjour helps you add a new printer to a local network without your configuration. Say we want to add a new printer to the local network. With Bonjour, the printer starts to configure itself. It will ask a few questions in order to do this self-configuration. First, it will ask that, is anyone using this IP address? If no one replies, then the printer will take this IP address. Next, it will further ask, is anyone using this host name? If no one replies, then the printer will take this host name. And it will take a service instance name in the same way as it takes the IP address and the host name. So this new printer successfully configures itself. After this automatic configuration, the printer's IP address, host name, and service instance names are all unique in this local network. Besides automatic configuration, Bonjour can also help users to automatically discover available services in the local network. This is accomplished in two phases, as discovery and resolution. We still take the printer as our case. Let's see how a client can automatically find this newly added printer. When you want to find the printer, the operating system will ask the network, does anyone have a printer service? The printer will answer that I have a printer service and its service instance name is HP service 9FE5. This is the discovery phase. After discovery, our operating system now knows all the service instance names of all available printer services in the local network. And next is the phase of resolution. During this phase, the operating system will first ask, so on which host is this HP service? The printer will answer that it is on the host. It is on host named HP9FE5, the host the local. However, this host name cannot be used for connection. In order to connect, our operating system still needs to know the IP address of the printer. Then it will ask, what is the IP address of this host name? The printer will answer with its IP address. With this IP address, our operating system can now connect to the printer for future printing jobs. Now the operating system has saved this printer in your printing list for future printing. However, I have a question here for you. The printer has three attributes: IP address, host name, and service instance name. So, which of these three attributes do you think are saved for future printing? Apple gives the answer that applications store service instance names. So, if the IP address, port, or host name changed, the application can still connect. So it is the service instance name that is saved in your printer list for future printing. Next time, when you print to your saved printer, you print to a printer who owns this service name. And our system will go through the resolution phase again to connect to this saved printer. Look at this observation. A saved printer is a printer who owns the saved service name. Later, I will show you what this observation means to an attacker. In our attack, we assume that the adversary has control on one device in the local network. In this network, other devices are not infected at all. The adversary aims to intercept files transferred between other uninfected devices. So in our previous example of the printer, even if your Mac and your printer are not infected at all, is it possible that your printing documents will be stolen by someone else in this network. Let's see how we crack these zero configuration techniques. And Bonjour is our first target. On attacking Bonjour, I will show you two examples. The first is the attack to the printer case, and the second is the attack to a paid application on iOS, which is called PhotoSync. In the first attack to the printer case, as assumed in our adversary model, the iMac in the local network is controlled by malware. Other devices, including the printer, are not infected at all. The malware from the iMac will claim a service instance name. This service instance name is exactly the same with that of the victim printer. And to avoid this conflict, the printer will configure itself again to use another service instance name. Recall from our observation that the saved printer is a printer who owns the service instance name you saved. This name is now owned by the adversary. So whenever you print to your saved printer, your documents are actually sent to the malicious device. It then forwards this document to the victim printer, which enables a successful man-in-the-middle attack. So why this happens? We now know all three attributes of a printer may change. However, Apple treats one of them as a constant identifier. This is nonsense. Relying on some changing attributes for identification may always fail. Also, a more fundamental problem here is the lack of authentication in this protocol. Anyone can claim any of the three attributes. The protocol only guarantees no duplicates, but not security. So you may have a new question. If the service instance names are not saved, is it secure enough? The answer is no. Our second attack to the paid iOS application, PhotoSync, will explain why. As we have introduced, PhotoSync is a paid iOS application. It uses Bonjour to automatically synchronize photos between Mac and iPhone in the same local network. During synchronization, the photo sender acts as a client, and the receiver acts as a server. The client uses Bonjour to find the server and connect to the server for sending this photo. Different from the printer case, the PhotoSync client does not save the service instance names of the PhotoSync server during Bonjour. Instead, it goes through the whole Bonjour phases of discovery and resolution each time there is need for synchronization. The process of PhotoSync is similar to that of printer. Client first process for the server in the phase of discovery by sending a broadcast query. Please note that the dashed line in the figure means broadcast. And the server will respond with its service instance name, say ABCD. In the following resolution phase, the client further queries for the host name of this service. And the server responds with its host name, which is MacBook. And in the following resolution, the client further queries for the address of the host. Then the server responds with its address. With this address, the client is able to connect to the server for synchronizing data. However, even if the PhotoSync client does not save the service instance name of the server, it is still subject to man-in-the-middle attacks. A malware-infected device in the same local network can still spoof the client. This spoofing happens in the resolution phase. Based on what is resolved, the attacker can launch two kinds of spoofing attacks. One attack maps the victim server's service instance name to the attacker's host name. And another attack maps the victim server's host name to the attacker's IP address. In the first attack, when the client broadcasts to ask for the host name of the server of the service instance name, say ABCD, both the server and the attacker will respond with their own host name. However, the client cannot distinguish which one is the real server. Then it has 50% to connect to the attacker. And the attacker forwards the connection to the victim server, which enables a successful man-in-the-middle attack. In the second attack, when the client broadcasts to ask for the address of the server's host, both the server and the attacker will respond with their addresses. Also, the client cannot distinguish which one is the real one, and it has a 50% chance to connect to the attacker, and the attacker will forward this connection, which is a man-in-the-middle attack. Here is a demo of our attack to photosync. In this demo, you will see that when two devices use photosync to transfer photo, a malicious device can intercept this photo. On the left side is the victim receiver, and on the right side is the victim sender. And the MacBook in the middle is the attacker. And now you will see that the sender selects to send a file now. And both the sender and the receiver start to connect to each other. And both of them will say that they have successfully connected to each other, but actually they are connecting to the attacker in the middle. And the receiver now starts to receive the photo. And you can see that the photo transfer begins. You can see that the photo is intercepted by the malicious device, and we show the OS versions in our experiment. And you can see that the MacBook device name is not seen by both the victims. And we show the iOS versions. You can see that the victim receiver also gets this file, gets this photo, and it is the same photo as the one intercepted by the malicious device. Though we only show two attacks in this Bonjour, what we show here is not a application-specific or service-specific problem. These attacks can be applied to other services or applications using Bonjour. As I have said in our attack to the printer, the fundamental problem behind these attacks is a lack of authentication in the protocol. Anyone can claim any value of the identification attributes. The protocol only guarantees no duplicates, but not security. And then you may have a new question. Is it easy to provide a proper authentication in this zero configuration scenario? The answer is no. To explain why, let's take a look at our attack to another important and popular Apple service, which is called AirDrop. Here is Apple's description for AirDrop. With AirDrop, you can share photos, videos, websites, locations, and more with people nearby with an Apple device. To transfer a file by AirDrop, you just need to click the receiver on your screen, and AirDrop will help you deal with the device connection and file transfer automatically. And here is a quick video demo of the normal AirDrop process. When you want to use AirDrop, you only need to click the receiver on your screen, and the receiver now gets this file. The AirDrop will handle the device discovery and the device connection automatically without your configuration. So, what is behind this quick demo? The AirDrop process also follows Bonjour. Say a MacBook wants to drop a file to an iPhone. It will first ask, does anyone have an airdrop service? Alice iPhone will say that I have one and its service instance name is ABCD. The MacBook will then ask, so on which host is this Alice service? If there is an aggressive attacker on this network, it will reply that this service is on Bob's Mac. And the victim iPhone will also reply with its host name. Chances are the victim MacBook may think that Alice's iPhone has a service named ABCD, which is on Bob's host, which enables the attack now. That is, the MacBook airdrops files to the attacker, and the attacker forwards the files to the victim iPhone. One thing you should know about airdrop is that airdrop sender will establish a TLS connection to a HTTPS server on the receiver's host. Now you may have a new question. Since this airdrop communication is based on TLS, does TLS help to prevent this attack? The answer is no. When you connect to the malicious device Bob using HTTPS, you will find that the malicious device is using a certificate issued to Apple ID.CDEF5678. This is a valid certificate issued by Apple. The only problem here is that it is issued to some Apple account, but you have no idea who is the owner of this Apple account. However, even if you are connecting to the right device, you will face the same problem. When you connect to Alice's iPhone, you will find that Alice is using a certificate issued to Apple ID.ABCD1234, but you really don't know who is the user behind this Apple ID. So according to Apple's design, the certificate here can hardly be used for authentication. To better understand what's going on here, let's take a look at how a certificate can be used for authentication in traditional HTTPS scenario. When you connect to google.com, your browser will find that the HTTPS server is using a certificate issued to google.com. Your browser will make sure that the domain you want to connect matches the certificate. However, in AirDrop, you'll find that even if you are connecting to the right device, the domain will never match the certificate. So, in order to make AirDrops work, Apple just skips the authentication. So, even with TLS, AirDrop still cannot provide the proper authentication. The problem is that the certificate in AirDrop cannot be used for authentication. In order to authenticate properly, the certificate should really be issued to a user, for example, Alice. But indeed, in AirDrop, it is issued to some meaningless random string as Apple ID.ABCD1234. So here is the question. What should this certificate be issued to? Since the certificate does not match the domain, can we just issue the certificate to the domain? No. The domain may always change and it cannot represent a user. See, how about we issue the certificate to the user's name? No. The user's name can be duplicated. And can we issue the certificate to the user's social security number? Of course, no. Because social security number for user is too private. So we now know that linking a human to her certificate is complicated. We need to find some identifiable information that is well-known, no privacy, and unique. We believe that this is still an open question, and we made our first attempt to address it, which will be explained later. Here is a demo of our attack to AirDrop. In this demo, two devices use AirDrop to transfer file. A malicious device can intercept this file. On the left side is the sender, and on the right side is the victim receiver, and the MacBook in the middle is the attacker. And we show the OS versions during our experiment. And now we start the malicious application on the Mac. And the sender now starts to send a photo. You can see that the photo is intercepted by this malicious MacBook now. And the receiver also gets this photo. You can see they are the same photo. So any files or URLs transferred through AirDrop can be intercepted in this way. When cracking AirDrop, we reverse engineered the AirDrop service daemon, which is sharing-D. Sharing-D is responsible for the whole AirDrop process, including the Bonjour process and the HTTPS connection. One interesting thing we found in AirDrop is that AirDrop does not use the normal Ethernet interface. Instead, it uses a specific Apple private interface, which is called AWS0. By using this AWS0 interface, AirDrop can establish device-to-device direct Wi-Fi link. So, in order to have launch a successful attack, we also need to spoof on this interface. Then how can we work on this interface? The answer is in sharing-D daemon. We found that it uses an Apple private socket option. With this option, we can now work on this AWS0 interface. Besides Bonjour and AirDrop, Apple also provides some frameworks to provide the capability to work with zero configuration. Next, let's look into a vulnerable framework, which is called multi-peer connectivity. Multi-peer connectivity is a framework for automatic service discovery. With the help of multi-peer connectivity, nearby devices can discover each other without user's configuration. It can work both on Wi-Fi and Bluetooth channels. It uses an object called PID to identify each application using this framework. PID has a few properties. One public property is called display name, which is customized by users or developers. And another private property called unique ID, which is generated by IMC and transparent to developers. During normal service discovery, the servers will advertise their PID objects. And the client will browse for these advertised PIDs and present these PIDs display names. Even if different servers' PIDs are created with the same display name, the unique IDs generated by IMC will always be different. As a result, the client can distinguish them by the unique IDs and show two pairs. However, when an attacker acts as both client and server, it will also browse and acquire the PID object advertised by the victim server. Then it can advertise using exactly the same PID object. However, the victim client cannot distinguish these two pairs because they have the same unique ID. It will consider that the attacker's PID is just an update to the existing one. And it will map the only PID to the attacker's address, which enables a man-in-the-middle attack. Here is our code to attack applications using multi-peer connectivity. We first start a browser looking for available advertisers. Once we find an advertiser using once we found an advertiser in this callback method, we start a new advertiser using exactly the same PID object and other advertised information. But if application do not use PID for identification, will they be secure? The answer is no. To understand why, let's take a look at another application which uses multi-peer connectivity framework but does not rely on PID for identification. Our target application is a very popular instant messaging software in China, which is named QQ. According to Wikipedia, QQ has more than 800 million active accounts now. QQ on iOS provides an interesting functionality, which is called face-to-face transfer. With this functionality, users can transfer files between nearby devices without need to connect to remote QQ servers. This functionality is based on multi-peer connectivity. Different from other applications using multi-peer connectivity, which uses PID for identification. QQ uses a customized, unique QQ ID for identification. Normally, at the beginning of each transfer, besides advertising PIDs, the file receivers also advertise their unique QQ IDs. And the sender browses for these QQ IDs. Once the sender finds the receivers, it will list the receivers according to their QQ IDs instead of unique IDs. Then the sender will connect to those receivers, and the sender will also need to send its QQ ID. The receivers now know which sender is connecting to them, and then the first file transfer will begin. However, when there is an attacker in this scenario, it will also find the receiver and the receiver's QQ ID, and it can advertise using exactly the same QQ ID. Then the sender cannot distinguish these two devices because they have the same QQ ID. And then it has 50% to connect to the attacker. The attacker will forward the connection to the victim receiver, which when connecting to the victim receiver, it uses the same QQ ID as the sender to pretend to be the victim sender, which enables a man-in-the-middle attack. So let's see our demo to the attack to QQ. When two devices use QQ to transfer file, a malicious device can intercept this file. On the left hand is the sender, on the right side is the receiver, and the iPhone in the middle is the attacker. And now the sender starts to send a file using this face-to-face transfer. And you can see that the file is now intercepted by the attacker in the middle. And we will try again to see whether it is. Yes, we try again. And we can see that the file is still intercepted by this attacker. And you will see that the files are the same. So this means a successful man-in-the-middle attack. You will see that they are the same. We show the QQ versions in our experiment and the OS versions. Zero configuration does not only apply to local network. There are also some zero configuration techniques in Bluetooth. For example, handoff. Handoff is a service that lets iOS and OS X synchronize data through Bluetooth without a user's configuration. Apple describes a handoff as follows. With handoff, you can start a document, email, or message on one device and pick up where you left off from another device. Handoff is based on Bluetooth Low Energy technique, which is short for BLE. It employs the out-of-band pairing method of BLE to pair two devices. Different from traditional Bluetooth classics, this pairing method does not require you to enter PIN code or do some other manual configuration work. The secrets for pairing in this method are changed through other channels instead of Bluetooth channel. And this pairing method also provides a secure connection between the paired devices, which prevents the man-in-the-middle attacks. Normally, when the iPhone and the Mac are logged in with the same iCloud account, handoff will establish a Bluetooth channel between these two devices automatically by this out-of-band method. The handoff service on these two devices will use this Bluetooth channel to synchronize data. Though this secured Bluetooth channel prevents man-in-the-middle attacks, we still find a critical vulnerability. That is, the Bluetooth channel does not provide application-level authentication. As a result, any advertised Bluetooth service on the iPhone is completely exposed to any app on the Mac. Among these exposed Bluetooth services, there is a service called ANSS, which is short for Apple Notification Center Service. ANSS is designed for Bluetooth devices to access notifications on iOS devices. With the help of ANSS, you can now read your iPhone notification on your smartwatch. So just as I have said, because there is no application-level authentication on this Bluetooth channel, this ANSS service is also exposed to any app on the Mac. When there is a malicious device with just Bluetooth capability on this Mac, it can also access the ANSS service through the Bluetooth channel created by handoff. Then it can get every notification on your iPhone from ANSS, including sensitive information like messages, emails. Here's our demo of the attack to this handoff case. In this case, you will find that when a handoff starts, a malicious app on the OS X can intercept notifications on the iPhone. Here we show the OS versions. And you can see that the two devices are now logged in with the same iCloud account. And we will start handoff. We will enable handoff on the iPhone, and we now start the malicious app on the OS X. And when a handoff starts, and there is a message coming, you can see that the malicious app on the MacBook can also steal this notification. You can see that this is just the same notification. That's our attack. In summary, we presented several attacks on zero configuration channels, including Bonjour, AirDrop, handoff, and multi-peer connectivity. All these vulnerabilities were reported to vendors, and most of them have been acknowledged by the vendors. To understand the impact of the security risks in Apple zero configuration techniques, we performed a measurement study. We analyzed the 61 popular Mac and iOS applications designed to operate without configuration. Among them, nearly 90% are vulnerable to man-in-the-middle attacks or impersonation attacks. The measurement result is shown in this table. For example, in the Bonjour channel, we sampled 22 applications, and among them, 18 are vulnerable. By exploiting these vulnerabilities, the attacker can steal sensitive information like files transferred, documents printed, or instant messaging. So we need to think about how to protect these zero configuration techniques. Here, we mainly show how we mainly show how we address the problem proposed in airdrop. That is, how to link a human to her certificate. As explained in airdrop, we need to find some identifiable but non-sensitive information from the user, which also needs to be well known to her contacts. Our solution is called SPACY, which uses the user's web biometrics to tag her certificate to her identity. In our solution, we first compute the hash value of the user's certificate. Then we take the NK most significant bits and then partition them into K segments. Each segment is then transferred to a rare but pronounceable word. At last, we let the user speak out these words, and in this way, we link the user to her certificate. So we conducted a human subject study, which shows that our solution is well received by users and effective to use. So in conclusion, our research shows that Apple zero configuration techniques are not secure at all. This usability-oriented design of zero configuration totally affects its security design. However, addressing such security risks is non-trivial due to the challenge in binding a human to her certificate. We proposed a voice biometrics-based approach called SPACY, which uses the user's voice biometrics to tag her certificate. So that's all. Thank you.